Hi, everybody. Today we're doing section or this video, I should say, is doing section 2.7. And the title of 2.7 is optimization. Before I start, I want to, I want to, boy, I can't talk anymore. I want to start with a couple of definitions. This may seem a little random, but it's actually quite critical. Um, and the first definition is something called a critical number. A critical number for a function is a value um, x equals a, and it has to be part of the domain of the function. And it has to be a number, to be a critical number, it has to be a number where f prime of a equals 0, or f prime of a is undefined. So if either of those are true, if f prime of a is 0 or if f prime of a is undefined, then that is a critical number. And I'll give an example in just a minute. But a critical point for a function, that's the point a comma f of a, where a is a critical number. In other words, once you get in other words, these two things are kind of the same thing, or they're talking about the same thing. The critical number, once you get a number where the derivative at that point at that value equals 0, so you just take that value and plug it into the function, and you get a comma f a, and that's your critical. But let me give you let me give you an actual example. So I'm going to switch projectors now. I'm going to go to okay, here we go. And I'm going to stop sharing the screen so now you can, okay, very good, perfect. This is an example at y equals x squared minus 2x. Now, y prime is equal to 2x minus 2, which of course is equal to 2 times x minus 1. Now, we see from this that if x equals 1, then y prime is going to equal 0, because y prime is going to be 2 times 1 minus 1, which is 0. So x equals 1 is a critical number. And now let me plug in 1. So if I plug in 1, I get 1 squared minus 2 times 1, which is 1 minus 2, which is negative 1. So 1 comma negative 1 is a critical point. So x equals 1 is the critical number, and 1 comma negative 1 is the critical point. And critical, this may or may not seem all that important, but it's actually going to be, pardon the expression, critical. See what I did there? I kind of did a play on words. Now I want to switch to another idea, a concept that we need to understand, which is also going to be crucial, and in our goal of optimization. And then I'll explain what optimization is all about. So let me switch. So I want to suppose we have a function y equals f of x, and let's say the graph looks something like that. Oh, it actually worked. And this point here, the low point on the graph. It's hard to tell the way I drew it. Oh boy, okay, that's the low point right there. Okay, and this really is a very distracting. Camera keeps on going out of focus. I looked up all the instructions of what to do, and I spoke to people, and somehow this camera keeps on going out of focus. Oh, good. All right. I want you to notice that when we're at the left of this point, if I would take any tangents, the tangents, if you notice, they're going downwards and have a negative slope. Negative slope. And when I'm on the other side, on the right side of this point, the tangents have a positive slope. Now at the point itself, at this bottom point itself, the tangent is straight horizontal, so it's a zero slope. The tangent has a zero slope. It focuses. So notice that when you have a minimum point, the slope on one side is negative because the function is going down, and then on the function the slope on the other side is positive. Now let's say on the other hand, let's say we had a different function, I don't know, y equals g of x, and g of x when I graph it, it looks like this. So here I have the top point. Well, again, you see that the slope is zero. It's a zero slope. And if I take a point on the right side, it's this has a negative slope. And I take a point on the left side, this has a positive slope. So if you notice, if I could just summarize these two functions here. So for this guy over here, and I'm going to call this point will be my A. And that's my A. So when when x is what the y prime is, it's a negative slope, so y prime is less than zero when x is less than a, y prime equals zero when x equals a, and y prime is greater than zero when x is greater than a. And this is the same idea. It's going to be different. It's going to be flipped around, but it's the same idea. Now, it wasn't so. I want to just point out one other thing here is that suppose the crucial thing here is that it's negative on one side and positive on the other side. And here it's positive on one and negative on the other. That's what's really crucial. The zero slope in the middle is not the most important thing for what I'm trying to do here. But what I'm saying here, what this is called, we're calling this a local min. Min stands for minimum. And this over here, this point over here, is a local max. Now, why am I saying that the negative, positive, positive, negative, that's the important part, and the zero part at the actual min and at the actual, why am I saying that's not the crucial thing here? Well, I'll show you why. Suppose I have a function that looks like this. Suppose I have a function, V-shaped function. So the slope is negative this side, slope is positive on that side, and the slope over here, the slope does not is undefined. It's an undefined slope because you can't. What's the tangent? Is that the tangent? Is that the tangent? Is that what's the tangent? It's undefined. It's an undefined slope. Plus, it could be undefined. It could be undefined for other reasons. Because when I come in from this side, I get that way. When I come from this side, I get that way. There's a lot of reasons why this point is an undefined slope. Nonetheless, it is a min. It is still a local min. Because it is the lowest point on the graph, which you can hardly see now. Anyway, this is leading up to something which I'm going to give you in a formal, official way. But I just wanted I want to give you a couple more diagrams here of concepts. I want to give you the concept. I guess it's a term called Extrema. Let me switch cameras here. And here we go. Okay, and now I want to share my screen. And that's not what I want. I want this. I want this right there. Okay. So when I say extremes or extrema, that means it could be a max or a min. So what we just did sort of, in a casual way is really called the first derivative test for extrema. For me, what I'm calling maxes and mins. And so here's how it goes. For each critical number C, if you examine the sign of f prime to the left and to the right of C, what happens to the sign as you move from left to right? Well, if f prime of x changes from positive to negative at that crucial point C, then C is going to be a local maximum at the point C comma f of C. On the other hand, if f prime of C changes from negative to positive, as we saw in our diagram, when x equals C, then f has a local minimum at the point C comma f of C. If f prime does not change sign at all, and I'm going to give you an example of that as well, then this point is neither a max nor a min. So I'm going to give you a whole bunch of examples now. I'm going to give you a whole bunch of examples of this idea. So let's get down right to it. Let's get next. I have to switch cameras again. So let me just do that here, and let me get ready to rock and roll. So this camera. Now we're ready to rock and roll. Let's suppose we want to find the local extrema of the function y equals x cubed minus 6x squared plus 9x plus 2. Well, the first thing I'm going to do is take a derivative. And when we take the derivative, we get y prime is equal to 3x squared minus 12x plus 9, because x to the third, to bring the 3 out in front, then drop the 3 down to a 2, it's 3x squared. 2 times 6 is 12, or in this case, minus 12. And then plus 9x becomes plus 9, and the plus 2 in the end just disappears. Now, everything here is a 3, so I'm going to factor out the common, the GCF of 3. And this is 3 times x squared minus 4x plus 3. Now, this quadratic here in the parentheses can be factored, and it factors into x minus 1 times x minus 3. So we see that y prime is equal to 0 when x is equal to 1 and 3. Because if x is 1, I have 1 minus 1 over here. If x is 3, I have 3 minus 3 over here, and pow. So 1 and 3 are the critical numbers of this function. Now I want to find, are these critical? Now, just because it's a critical number doesn't necessarily mean it's a max or a min. Because as we saw in the definition, now we haven't seen a case like that yet, but we'll show you that later. In this video, how do we know if it's a max or min? Well, we have to check what the derivatives are before and after these points. So so what we do is a nice, easy way to do this, nice, simple, nice, straightforward way to do this is that we take the number line and we take the critical points 1 and 3. And we use those points to divide the number line into 1, 2, in this case, 3 separate intervals. So this whole interval, I'll call it A, that interval I call it B, that interval I call it C. And we want to look at the derivative if it's positive or negative in these intervals. So what I do is I take test points. So here I took a test point of 0 because it's less than 1. Here I took a test point of 2 because it's in between 1 and 3. And here I took a test point of 4 because it's higher than 3. And what I do is I take this test point and I plug it into the derivative. Well, when I plug in x equals 0, I get 3 times negative 1 times negative 3, which is positive 9, which is a positive number. So put a big plus there. Now I test out x equals 2 because that's this interval. So when x equals 2, again, I plug that into y prime, and that gives me 3 times 2 minus 1 times 2 minus 3, which is negative 3, which is a negative number, and there we go. I'm less concerned about the 3. I'm more concerned about the fact that it's negative. and I'm more concerned that that's a positive number. Well, if that was 9, 11, 15, 112, it doesn't matter. That's not relevant at this juncture. Uh, it's just I just want to know if it's positive or negative. I'm not saying it's irrelevant completely, but for what we're looking for at the moment, it's all I care is that it's positive. And now I plug in x equals 4. That's my last test point. So I get 3 times 4 minus 1 times 4 minus 3, which winds up to be 9. 3 times 3 times 1, which winds up to be 9. And it all works out. So I have a positive, negative, and a positive. Now, let's go back to the critical number 1. I see it's positive before and negative after. That means this is a max, because it's going up the hill, hits the max, and comes down the hill. Positive, negative. Here I have negative, positive, around the 0.3, so that's a min because it's going down negatively, then it goes up positively, and there we go. So now 3 and 1 are critical numbers, which happen to yield maxes and mins. But what are the critical points? So for the critical point, I have to take each of these values separately. I take 1, and then I'm going to take 3, and I'm going to plug them into plug them in for x. But where am I plugging them in? Am I plugging it in here, there, there, there? Where do I plug it in? The answer is I plug it into the y, because I'm plugging it into the original function. I want to know on the original function, is this a maximum or a minimum? So I plug in 1. We'll do that one first. When I plug 1 into the original function, I get 1 to the third. Let me just show you here. 1 to the third minus 6 times 1 squared plus 9 times 1 plus 2, which is 1 minus 6 plus 9 plus 2, which comes out to grand total of 6. So the point 1 comma 6, that is my critical point. That's a critical point. And it happens to be a max, and it happens to be a max. So 1 comma 6 is my critical point. X equals 1 is my critical number. 1 comma 6 is my critical point, and they make a max. Let's try the other critical point was 3, so I'm going to plug that in to our equation. So we get x equals 3. Now I know it's going to be a min. We already know that. We established that by looking at the slopes before and after. So let's actually find the value. So it's going to be 3 to the third minus 6 times 3 squared plus 9 times 3 plus 2. That's 27 minus 54 plus 27 plus 2. And that comes out to a grand total of 2. So my critical point is going to be 3 comma 2. So 1 comma 6 is my critical point, which is the min, and 3 comma 2 is my critical point, which is a a max. I'm sorry, vice versa. 1 comma 6 is the max, and 3 comma 2 is the min. I want to graph this on Desmos, and let's see what this looks like. So I'm going to, what am I going to do? I have to switch cameras again. And share my screen. And I'm going to go to Desmos. I'm going to put in y equals x to the third. And that's minus 6x squared, minus 6x squared plus 9x and plus 2. And if we look here, we see that our our local max is 1 comma 6 and 3 comma 2. 1 comma 6 and 3 comma 2. And these are our local maxes. So let me go back. Is that beautiful? Is that a beautiful site? So it all works out beautifully. It all works out perfectly. Okay. As long as you're here with Desmos, I want to show you a nice example. Actually, I want to show, first I want to show it to you with algebra, then I'll show the actual actual working out the numbers. Then we'll come back. So let's stop the share. And let's call this a switch cameras. Okay. And I do want to point out this is a local max and a local min. Local max, local min. Okay, let's look at a oops, of a function. Well, let's look at y equals x to the third power. And I want to find the extrema. So y prime, the local extrema, y prime is equal to 3x squared, which I'm going to set equal to 0, which implies that x has to equal 0. So x is my critical point. X is a point where I said x is a point where the derivative is equal to 0 at 0. So if I look before, let's say I take -1 and +1 as my test points, because this one point breaks the number line into two regions, two intervals. So I'm testing my derivative, y equals 3x squared. I want to see if it's positive or negative. If x is equal to -1, it's 3 times -1 squared, which is +3. So I put a positive up there. And if x is equal to +1, I get 3 times 1 squared, which is also 3. So positive, positive. So because it doesn't change signs, it stays the same. The sign stays the same. Therefore, it is neither a max nor a min. So 0, or in this case 0 comma 0, is neither a max or a min. And how is that going to, I should say, a local max or a local min? Let's let's take a look at the graph, and we'll see if we can get some insight into this. So here's my graph. I gotta share my screen. Here we go. So I'm just gonna actually I want to do something. I want to take a picture of this page. Okay, now I'm gonna go and let's make this a little bigger so you can see a little better. Okay, so if you notice, the derivative is positive because the slope is the function's going up is increasing, and therefore each tangent line would be in a positive direction. And here the tangent kind of flattens out and becomes completely horizontal because the slope is 0. But then instead of going down again at that point, it's horizontal, but then it continues going up again. So I have positive slopes because we're going up, and I have positive slopes here because we continue going up. Even though it's a 0, it's kind of like it gets there, it kind of teeters, but it could just as easily have gone down, but instead it goes up, 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 up and away, I should say. And now I want to show you another idea. We're talking about maxes now, maxes and whatnot. So let's say we have a function that looks like this. Well, this point here is a local max, but it's not a global max because it's not the highest point on the entire graph. It's the highest point in its little neighborhood. If you look at the little neighborhood around that point, it's the highest. It's the highest point. It's the greatest, y value. Um, but it's not the global max because the global max would be up here. Because up here, for example, you have the highest point in the entire function. And this point down here is the local min, but it's not the global min. Global min would be over here. Now, of course, I could have an example like this guy over here, where so this point up here is local and global max. This point down there is the local and the global. And this is that's just a local min, and that's a local max, etc. So all these things are possible. So a point, a local max might be a global max, might not be a global max. It all depends on the particular graph, depends on the particular function. So that's the but I just want to say a fun and important fact is that a local max or a local min can only occur at a critical point. A local max or a local min can only occur at a critical point. Let me write that down. A local max. Actually, the textbook has it beautifully. So let me just let's go. Let's switch cameras. I'm gonna share my screen. A local max or a local min. Here we go. A local max or min of f can only occur at a critical point. Now, as we saw, just because something is a critical point doesn't mean it will be a local max or local min. And we saw that with y equals x to the third power. So not every critical number will be a local max or a min, but every local max or min has to be a critical point. It can only occur at a critical point. I want to give you one last example in closing of a function. Well, I'm going to give you a function where a critical number where f prime is undefined. So let's. I showed you one where it's I showed you one example where it's kind of a jagged edge. I'll show you a different kind of example now where it's smooth but still undefined. So now I'm going to have to go back to my let's see. Okay, here we go. Okay, so I'm going to look at this function. I'm looking at y equals x to the third power. So we're going to look at the function y equals x to the 1/3 power. Now, if you're familiar with this function, the graph, it's kind of like a it's kind of like this, and if I would take the derivative y prime, the y prime equals 1/3 times x to the 1/3 minus 1, which is the same thing as 1/3 x to the 1/3 minus 3/3, which is the same thing as 1/3 x to the negative 2/3. But another way of writing this, which makes it more obvious, is that this is y prime equals 1/3 times x to the 2/3 power. Now, if x is equal to 0, y prime of 0 is going to be 1/0, which everybody knows is undefined. Undefined. Let's look at a graph of that. Now on my graph, I really drew a horrible graph. If there was a good graph, you'd see it a lot better. So let's go to Desmos. They draw a lot better than I do. Okay, is this okay, here we are. Okay, so let's look at y equals x to the 1/3 power. Oops. Okay, so for y equals x to the 1/3 power, if you look at this more carefully, if you notice, the slope at 0 is 0. The slope is like a straight vertical line, and a straight vertical line is an undefined slope. And that's really what's happening here. So let's now go. Well, that's the example I want to show you. Okay, let's go back to here. So as you see, for x to the 1/3 power, when x is equal to 0, the slope really would become just a very straight vertical line. Basically, the y-axis would be the tangent at that point, because the slope is rising, and then rises very quickly and becomes straight, sheer vertical. And a vertical line, as you know, has an undefined slope. So that's what happens over there. The last thing I want to do for this, this is part 1 of the video. The last thing I want to do for part 1 is to remind us. We mentioned that when the second derivative, if f prime prime is positive, then the function is concave up, which is what this is right here, concave up. And when the second derivative is negative, then the function is concave down. So it looks like this. Well, if a function is concave up, that means this point right over here is a min. And if a function is concave down, that means that point is a max. And that is sorry. So if it's concave, if the second derivative is positive in the neighborhood of that point, it's going to be a min. If it's negative in the neighborhood of that point, it's going to be a max. Let's state this more formally. I'm going to switch cameras again. And this is actually known far and wide as the second derivative test for extremes. So if you find all the critical points of f, for those critical points where f prime of c equals 0, find f double prime of c. If f double prime of c is less than 0, then f is concave down and has a local max at x equals c. If x double prime is greater than 0, meaning it's positive, then the function is concave up and it has a local min at x equals c. Finally, if the second derivative is equal to 0, then it may be a max, it may be a min, it may be neither. It's inconclusive. If the second derivative equals 0, it is inconclusive. The test, I should say. And an example of inconclusive would be the function we just saw, y equals x to the 3rd power. Because even though the second derivative, well, let's actually show it. Let me just show you. I don't want to just talk. Let me just show you. So I'm going to have to switch cameras again. Okay, so Let's look at the examples we had earlier. We had an earlier example, y equals x to the third. Well, in that case, y prime is equal to 3x squared, and y double prime is equal to 6x. And y double, if I set that equal to 0, I get y double prime equals 0 when x equals 0. And because the second derivative is 0 and not, oh boy, I'm sorry, I messed this up badly. X double prime, we said x double prime equals to 0. I had a little lapse there, sorry about that. X double prime, x prime we set equal to 0, and that gives us x equals 0. But if I take the second derivative and I plug in x equals 0, I get 6 times 0 equals 0. And since the second derivative equals 0 at the critical number 0, therefore it is inconclusive whether it is a max or min. And we actually saw in Desmos that it's neither a max nor a min. We saw it's a function, it's like a, you know, the function is right in the middle of the, it was something like that, where wasn't a max or a min. Now let's look at the problem we had at the beginning of today. Let me just let's look at y equals x to the third minus 6x squared plus 9x plus 2. And remember, the critical numbers were x equals 1 and x equals 3. Those, we already found those critical numbers. So let's take y prime. Y prime is equal to 3x squared minus 12x plus 9. And y double prime is equal to 6x minus 12. 6x minus 12. Well, y double prime of 1 is equal to 6 minus 12, which is equal to negative 6, which is negative, so it's concave down, which means it looks like this, so it's a max. And y double prime of 3 is equal to 6 times 3 minus 12, which is 18 minus 12, which is 6, which is positive, of course. So it's concave up, which as we know looks like that. That's a min. And that's exactly what we got when we took the first derivative test. So we have the first derivative test, we have the second derivative test. So we have a nice arsenal of methods to determine if a function is if a point is a local max or a local min. And we're going to use this. We're going to use this for part 2 of our video to tackle problems called optimization problems. And I'll leave you in a little suspense, and we'll find out in our next video what exactly optimization is. And everybody, it's been wonderful. It's been fabulous. And we'll see you guys next time. Bye.